We need to calculate the posterior distribution for a model composing a normal likelihood with mean theta and known variance sigma squared, with a normal prior distribution for theta with hyperparameters mu0 and tau0. To get started, we apply Bayes' rule. It tells us that the posterior is equal to the likelihood, in purple, multiplied by the prior, in green, divided by the evidence. In Bayesian computation, we can often work with the unnormalized posterior distribution. If we consider the posterior distribution a function of theta, then dropping all terms that don't depend on it gives this proportional density. This density does not integrate to 1, but its shape is unchanged. Let's start by writing out the likelihood multiplied by the prior. If we have n independent data points, this is a product of normal distributions with mean theta and variance sigma squared. Multiplied by the prior, a single normal distribution with mean mu0 and variance tau squared. We can separate the normalization constants in both the likelihood and the prior from the calculation because these do not depend on theta. There is a product of n of these from the likelihood and one from the prior. We can then simplify the expression involving a product of exponentials by combining the exponents in a sum. Let's call the product of these constants C1. Following this, we can expand out the quadratic terms. Doing so reveals some more constants. These can be separated and combined with the constant C1. We now have an exponent with 4 terms involving theta squared and theta that can be simplified. In a conjugate model, the posterior distribution belongs to the same family as the prior distribution. So far, we have derived the following proportional posterior. If a normal distribution is a conjugate prior for theta in this model, then the posterior distribution must be proportional to the exponential of a quadratic term involving theta. To demonstrate this, we can match the form of the normal distribution in our expression and identify the posterior mean and variance. Looking at the first term, we can read off the value for the posterior variance. Similarly, we see that the coefficient of 2 theta is equal to the posterior mean divided by the posterior variance. The posterior mean must be equal to this value multiplied by the posterior variance. With these two terms, we now know how to write the posterior in the form of a normal distribution. By plotting the posterior distribution for theta, we can gain valuable insight into the Bayesian computation. The setup for the plot is as follows. Take 10 independent samples from a normal distribution, with a mean of 70 and a standard deviation of 2. Set the prior mean to 70 and the variance of the likelihood to 4. On the x-axis is the prior standard deviation, and on the y-axis is theta. Important reference lines have been plotted on the graph. The prior mean, the sample mean, and the posterior mean. The shaded area around the posterior mean captures the uncertainty in the posterior. The prior is very strong when tau is close to 0. As tau increases, the prior weakens to allow the information in the likelihood to propagate into the posterior. We can see this by noting the approximate values for the posterior mean and variance at these extreme points. Near 0, the posterior mean is unchanged from the prior value, and the uncertainty is tiny. When tau equals 10, the posterior mean is approximately the sample mean. And the posterior standard deviation is the standard error of the mean. A result very similar to the maximum likelihood estimate. Using the same data as before, but fixing the prior standard deviation to 1, a similar plot can be created for the likelihood. The same reference lines have been drawn again. When sigma is close to 0, the likelihood is strong, gradually weakening as it increases. When the likelihood is strong, the posterior mean equals the sample mean, and the uncertainty in theta is tiny. Conversely, when the likelihood is weak compared to the prior distribution, the posterior distribution is approximately the prior distribution. In both plots, we see that the compromise between prior and posterior depends on the relationship between the likelihood and prior variance. This makes sense because the posterior mean is a weighted mean, where the weights are directly related to these variances. In this model, the compromise between information in the likelihood and information in the prior, characteristic of Bayesian computation, happens when neither of these weights dominates the computation. This is where the rate of change of the posterior mean is large, where the interesting interpolation between the two competing components occurs.